So in today's video, we're going to be looking at chapter 6.5, which looks at least squares problems. What this does is when you get a real world problem and it's based on linear equations, so you have a system of linear equations that will represent something in this real world problem and you want to solve it. So what we've been looking at is systems of the form ax is equal to b. Okay, so you've written your linear equations in this form. The problem that you have, and we've seen this in some of the systems that we've solved, this isn't always consistent. And especially in real world problems, you can't guarantee that you're going to come up with this system that is going to be consistent. So what they tend to do, if it is an inconsistent system, is they try and find something called the least squares solution. And what that is to find some x that makes a times x as close to this b as you can possibly get, such that the system is still consistent. Okay, so if a times x is equal to b is an inconsistent system, we try to find, we tend to call it x hat for this closest solution that we can find. We try to find an x hat such that a times x hat is as close to b as we can find. Okay, so in order to find that x hat, what you are trying to do is you are trying to minimize the difference between b and a times x. Okay, so what you're trying to do is minimize the distance between b and a times x, because if you can minimize that distance, then it means that a times x is as close to b as you can possibly get. So the solution to minimizing b minus ax, the solution to that, the x that solves that, is x hat. So when you minimize b minus ax and take its magnitude, when you minimize that magnitude, the smallest magnitude that you can find is always found at this x hat solution. Okay, so if you take A as an n by n matrix and B would be an Rm, then the least squares solution of A times x is equal to b is x hat in Rn such that the distance between b and ax hat is smaller, it's less than or equal to, when you multiply a by any other x and subtract that from b, that is always going to be larger than the distance between b and ax hat. Okay. So what are we effectively looking at here if we look at it like graphically? Well, we know that ax hat must be in the column space of A. Okay, because ax hat, okay, exists in the column space of A. The reason being, all you are doing, x hat would just be the coefficients of the columns of A. So you are just taking some linear combination of the columns of A, so A times x hat must be in the column space of A. So what you are doing here is you are finding the x hat that would make A times x hat the closest point in the column space of A to B. Okay, so if you had, let's say, the column, this is going to be a really bad drawing and it's not really too accurate, but to kind of show you what I'm saying here. If you had this as your column space of A, okay, this was the space that was spanned by the column space of A. In this case, it's a plane, so you'd only have two columns, but If this was our column space of A and this was your vector B, such that A times X is equal to B was your system, okay, and this was the column space of A, the X hat, okay, is such a point such that A times X hat is the closest point on the column space of A to B, okay? Because if you were to take A times any other vector X, you get another point in the column space of A, but it would be further away from B. So X hat is the vector that makes A times X hat the closest point that lands in the column space of A to B, okay? Because B would not land in the column space of A if A times X equals B is inconsistent, okay? If the space is consistent, okay, if A times X is equal to B is consistent, then B is in the column space of A. But when that system is inconsistent, then we know that B is not in the column space of A, but the challenge is to find that X hat so that A times X hat is as close to B as it can possibly get in that column space of A. So how do we find X hat? How do we find this vector X hat? Well, we know, okay, let's say that B hat is the projection of B onto the column space of A, okay? So define B hat as the projection of B onto the column space of A. So you can also write that as the projection onto the column space of A of B, okay? So by definition of these projections that we've been looking at, particularly in 6.2 and 6.3, we know that B hat would be the closest point to B that lands in the column space of A. So therefore we know that AX is equal to B hat must be a consistent system because B hat is in the column space of A. Because it's the projection of B into the column space of A, so we know that B hat is in the column space of A. Therefore, we know that A times X is equal to B hat is a consistent system. Now, again, by definition of what we've just called B hat, okay, it's the closest point to B that lands in the column space of A because it's a projection, so it must be the closest point to B that lands in that space. So therefore, we know that the solution to this system would be X hat. Okay, X hat must be the solution. So we know that A times X hat would equal that B hat vector. Okay, so in order to find X hat, okay, we know X hat is the solution to the system A times X is equal to B hat, where B hat is the projection of B onto the column space of A. So what else do we know about this system? Okay, we know already that X hat is this solution, okay? Now, the other thing that we know, which will make it really easy to find this X hat, is going back to the orthogonal decomposition theorem in chapter 6.3, okay? Where we looked at taking some vector Y and splitting it into the sum of two vectors that were orthogonal to one another. One of which was the projection of the vector Y onto this space. We called it W. In this case, we're going to look at the column space of A. So one of these vectors was Y hat, which projected Y onto that space W, and then some vector Z that was orthogonal to that Y hat. We're going to do very much the same here, okay? We know that B hat is the projection of B onto the column space of A, okay? So we already have this projection vector B hat. The vector that is orthogonal to B hat, if you go back to that orthogonal decomposition theorem, it's actually on page 350. There's a picture of this that will show it as well on page 350, the vector that was orthogonal to that y hat was this vector z hat. Was this vector z, sorry, and z was equal to y minus y hat. Okay, so when we broke a vector up into the sum of two orthogonal vectors, so y hat and z were orthogonal to one another, this y hat was the projection of y onto this space w, and z was orthogonal to that vector y hat. It was orthogonal to that space w, okay? And z, if you rearrange this, was y minus y hat, okay? Same thing here, okay? We're going to take this vector b and we've projected it onto the column space of A. And that gave us b hat, okay? Then the vector that is orthogonal to that column space of A is going to be this vector z, which would be b minus b hat. So we know, if you look at that figure 2 on page 350 that looks at this orthogonal decomposition theorem, it would mean that b minus b hat, in our case, where b hat was the projection of b onto the column space of A, this vector here is orthogonal to the column space of A. Okay, in the same way that y minus y hat was orthogonal to y hat, it was orthogonal to that space W. Okay, so that must mean that this b minus b hat must be orthogonal to every column in A. Okay, if it's orthogonal to the whole space, it must be orthogonal to any vector that lands in that space. So you take the dot product of b minus b hat with any column of A or any linear combination of the columns of A, and you would get 0. So I can say that b minus b hat, okay, I'm going to rewrite this in order to do this, would be b minus a times x hat. But if I take the dot product of that with any column of A, I should get 0. So if I take some column of A, we'll call it AI, dotted with b minus ax hat, I should get 0, okay? Which would mean a dot product is the same thing as taking the transpose of a vector and then multiplying it by the vector. So that's the same thing as saying AI transpose times b minus ax hat is equal to 0. That's exactly the same thing. Well, if I did this with every column of A, okay, I would end up with a 0 vector. So if I did the whole matrix A, okay, multiplied by this vector b minus ax hat, I should get the 0 vector, because for each one of those columns, I'm taking the column and transposing it to make it a row. So if I were to do A transpose times this vector, I should end up with the 0 vector, because I'm doing it just multiple times. Okay. Rearranging this, I would get A transpose B, or actually I'm going to do this the other way around. Okay, multiply this out, and I'm going to put the x hat on one side and the b on the other side. So I'm going to get A transpose A x hat is equal to A transpose B. Okay. So what do we have here? Well, if you look at this equation here, okay, what I can do is, just using that matrix A and the vector B, I now have a system in which I can find x hat that does not include any projections whatsoever. Okay, I don't have to find, because before we said, okay, well, I could just solve this equation. The problem is that I have to find that projection vector b hat, and finding projections involves dot products depending on how large that space is that you're projecting onto. So depending on how large a space the column space of A is, you've got to keep taking dot products of vectors and all of that, so it takes a while. So rather than finding that projection vector b hat and then doing a Gauss-Jordan reduction to find x hat, all I have to do here is use my initial matrix A and my initial vector b, and I can go ahead and solve this system to find x hat. All I have done here is taken A times x is equal to b, and then I have basically done something to it involving this transpose of A in order to solve this system that will give me that x hat, that least squares solution. So the easy way to find the least squares solution of ax is equal to b is instead to solve this system. So you find A transpose A, that's going to give you a square matrix. Then you find A transpose B, that's going to give you another column vector, and then you can go ahead and use Gauss-Jordan in order to find x hat. You don't have to look at any other projections, you don't have to take dot products of anything, you just have to look at that matrix and that vector, put them into an augmented matrix, use Gauss-Jordan and find x hat. So let's do an example of this. Okay. We're going to find the least squares solution for a times x is equal to b, where a is going to equal -1, 2, -1, 2, -3, 3, and b is going to equal 4, 1, 2. Okay. Now, we need to find the least squares solution, which means that we need to solve this equation, okay? A transpose A, okay, if you take the transpose of A and then multiply it by A using row times column when you do this, A transpose A is going to be 6, -11, -11, 22, okay? And then A transpose B, so taking the transpose of A and then multiplying it by this vector B, I get -4 and 11. Okay. So when we go ahead and put it into this system, what I'm effectively reducing is this augmented matrix. Okay. And therefore I'm solving for x hat. So if you do that and reduce this down, you can do it on a calculator. I get this. So that must mean that x hat is equal to 3, 2. Okay. So this is the vector that if I substituted it in for x, makes this as small as it can possibly be. This is the vector that makes the distance between a times x and b as small as it can possibly be. So this is basically my closest estimate to solving a times x is equal to b. Okay, because otherwise the system is inconsistent. You can do one of these systems and solving one of these where there are infinitely many solutions to x hat. That is totally fine. It's very difficult to see because you're dealing with like very large dimensions here. You're dealing beyond a 3-dimensional case. But when you are solving one of these and you end up with infinitely many solutions, what it is basically saying is you have something that's like a line where every point on that line is as close to the point B as you can get. Okay, so there are infinitely many points, whether it be on a line or on a plane, which again, I know it seems kind of counterintuitive and it's very difficult to see in more than a couple of dimensions. Like once you pass 2 or 3 dimensions, it's very difficult to visualize this. But what it's saying is therefore that every point on that plane is as close to B as you can possibly get. Okay. So let's expand this. There are a few things that you can say are equivalent statements that involve this least squares solution. Okay. The first thing, the equation a times x is equal to b has a unique least squares solution for each b in Rm. Okay, so how else can we phrase that? Well, we can say the columns of A are linearly independent. Okay, so if the columns of A are linearly independent, it means that no matter what your right-hand side B is, I'm always going to end up with this unique solution. Why? Because it makes A transpose A an invertible matrix. So if A has linearly independent columns, A transpose A is going to be an invertible matrix. A may not necessarily be invertible because it may not be a square matrix, but no matter what size of a matrix A transpose A is always going to be square, and it's always going to have linearly independent columns if A has linearly independent columns, which means that A transpose A is a square matrix with linearly independent columns. It's going to be invertible. So A transpose A is an invertible matrix, and therefore no matter what your right hand side B is, the solution X hat, the least squares solution, is given by A transpose A inverse times A transpose B. Okay, so all it means is that it gives you an easier way to solve this equation. A transpose A X hat is equal to A transpose B. If A has linearly independent columns, it means that A transpose A is going to be invertible, which means that X hat is going to have a unique solution no matter what the vector B is, and you can find that X hat by just inverting A transpose A, multiplying by that on both sides, and you get that X hat is going to equal A transpose A inverse times A transpose B. Okay. Okay, just another quick definition for you. The least squares error of the approximation. Okay, that is the distance between A times X hat and B. Okay, unless you have a consistent system, B minus AX hat is never going to equal 0. Okay, you're never going to get the 0 vector out of there, and therefore the magnitude is never going to be 0. There is always going to be some error when you have an inconsistent system. A times X is equal to B. Okay, no matter how close you can get to B by multiplying A with X hat, you're never going to get exactly 0 unless you have a consistent system. So that distance between B and AX hat is called the error of the approximation. It's the least squares error of the approximation. So going back to our example that we just did, okay, let's find that least squares error of the approximation. X hat was 3, 2, B was 4, 1, 2, and this was A. So if I go ahead and find B minus AX hat and taking its magnitude, this is for our previous example, I would get 4, 1, 2 minus negative 1, 2, negative 1, 2, negative 3, come back, 2, negative 3, 3, 3, 2, which is going to equal the magnitude of that vector when you multiply it out and subtract, which is going to be, the magnitude of this vector is the square of 3, which is 9, plus 1 squared is 1, plus negative 1 squared is 1. So it's the square root of 11, okay? That is as close to B as I can get by using that vector X hat and multiplying it by A. Okay, that is the distance between B and AX hat. So that is how far away B is from that column space of A, this closest distance. Okay, so we have done this where we've just used a random matrix A and we ended up with a system A times X is equal to B, which was inconsistent. So we tried to find that solution X hat that got us as close to a solution as we could possibly find. There are other ways of calculating this least square solution other than using this formula. Okay, there are other ways of calculating X hat instead of using that, but it depends on what that matrix A is. So we're going to look at two cases here. One of which is when the columns of A are orthogonal. The other is when the columns of A are just linearly independent. They don't necessarily have to be orthogonal. But each one of these gives you another way of calculating that vector X hat that's that least square solution. So the first one we're going to look at when the columns of A are orthogonal. So when the columns of A are orthogonal, how can we find this x hat? I'm going to do this by an example, okay? So let's do the example, finding the least squares solution of ax is equal to b, and a is going to be 1, negative 1, 1, 2, 4, 2. And b is going to be 3, negative 1, 5. Okay, so I want to find the least squares solution of this. If you take the dot product of the columns of A, you're going to get 0. So you know that the columns of A are orthogonal, so we can go ahead and find this least squares solution. But in this particular case, what can we do? Well, first thing I'm going to do is kind of going the long way that I was talking about earlier of finding that b hat vector, that projection of b onto the column space of A. Okay. Now, if you go back to when we did projections in 6.3, the way that we find the projection of B onto the column space of A is by using these dot products of B with each of the basis vectors in that column space of A. So, or in 6.3, we were just doing the projection onto a space W, so we took the dot product of the vector that we were looking at projecting, and we took the dot product of that vector with each of the basis vectors in W. So we're going to do the same type of thing here, where we're going to be taking B dotted with the first column of A over the first column of A dotted with itself times the first column of A plus B dotted with the second column of A over the second column of A dotted with the second column of A. Okay, so if you go ahead and do this, so you're taking B dot A1 over A1 dotted with A1 multiplied by A1, and then B dotted with A2, and then the same thing again. If you go ahead and do that, I'll tell you what you end up with. You should get 3 multiplied by 1, negative 1, 1, plus 1/2 multiplied by 2, 4, 2. Okay, if you do that, multiply those and add them together, I get 4, negative 1, 4. Okay, so that is my projection vector B hat. So that is the closest point to B that lands in the column space of A. So what you can then go ahead and do is to solve A x hat is equal to B hat. Okay, so you can go ahead and solve A x hat is equal to B hat. So what I'm solving there is 1, negative 1, 1, 2, 4, 2 times x1, x2, and we said that B hat is 4, negative 1, 4. Okay, but the reason that this is so nice when you're dealing with orthogonal columns of A is when you look at this system, what I am always doing is each of my entries in my first column of A ends up multiplying x1. And each of my entries in my second column of A ends up multiplying x2. And that is what gives me this vector. When I add those together, I get the vector B hat. So I'm doing the first column of A times x1 plus the second column of A multiplied by x2 should give me 4, negative 1, 4. Well, if we come back to what I did here, that is exactly what I have on this line here. By multiplying all this out, when I found B hat, I end up getting 3 times the first column of A plus 1/2 times the second column of A was that vector B hat. So what that tells me is that x1, oh, let me come back, sorry. x1 is equal to 3 and x2 is equal to 1/2, because that is what was multiplying the first and second columns of A to give me 4, negative 1, 4. So I already know that x hat is just that vector. Okay, So that is what is nice about having these orthogonal columns of A, is when you actually go ahead and find that projection vector B hat that projects B onto that column space of A. When you go ahead and find B hat, you actually solve the problem yourself, finding that X hat vector, okay? Because each of those coefficients of the columns of A is what forms that X hat vector. So that's what makes this so nice when you have orthogonal columns of A. The next type of problem I want to look at is when A has linearly independent columns. Okay, so they're not necessarily orthogonal, although when you do have orthogonal columns, it makes them linearly independent, as we've seen before when we looked at that in 6.2. But when A is linearly independent, well, when A has linearly independent columns, how else can we look at this? Well, we know that they're not necessarily orthogonal, so what else can we do with this? Well, going back to what we did when we did QR factorizations from the Gram-Schmidt process that we did in 6.4, okay? If A has linearly independent columns, I know that I can find a matrix Q and a matrix R such that A is equal to QR. A is an orthonormal matrix, okay? Its columns are orthonormal to one another. So this thing has orthonormal columns, and we found those using the Gram-Schmidt process. And then R was just this upper triangular matrix that had positive diagonal entries. Okay. So it actually turns out, and I'm going to do a very quick proof of this, it actually turns out that when A has linearly independent columns, so we can write the QR factorization of this matrix A, it turns out that the least squares solution of AX is equal to B when A has linearly independent columns is X hat is equal to R inverse Q transpose B. Okay. The question is why? Okay. Well, let's assume that X hat is equal to that vector. Okay, we've got two matrices multiplied by one another, multiplied by that vector, you're going to get another vector out. Okay, so assume that that is the solution. If I do A times X hat, okay, let's take the QR factorization of A multiplied by that vector. Okay, now if I redistribute these parentheses, I could say that I've got R times R inverse, that's going to give me I, the identity, so that can go away, and I will just get Q transpose B. Okay, now, if you go back, and this is using a very small theorem that comes out of 6.3, there was a thing that we looked at right at the end of 6.3 when we were looking at the properties of orthonormal matrices. And I went through this right at the very end. If you had, I think we used, I can't remember if I used a Q or a U when I did this, but in the textbook they use a U. If you have a matrix, in this case Q, that has orthonormal columns, okay, I can write the projection of W, the projection of Y onto W, sorry, is U transpose Y, where U is made up of these orthonormal basis vectors for W. Okay, now in the same way, I know when we did this QR factorization, let's say that the columns of A are going to span this column space of A. Okay, by definition, the columns of A span the column space of A. Because those vectors are linearly independent, I know that they form a basis for the column space of A. So in this case, because A has linearly independent columns, I know that the columns of A actually form a basis for the column space of A. Now, we said when we did QR factorizations that this matrix Q is made up of orthonormal columns, and they actually form an orthonormal basis for the column space of A. So because of that, I can do the same thing here, okay? I know that my columns in Q are going to form an orthonormal basis for my column space of A. So if I apply that same thing here, what I have on the right-hand side here is just this projection of this vector B onto the column space of A, because the columns of Q form an orthonormal basis for the column space of A. Okay, so all this thing on the right is B hat, because it's the projection of B onto the column space of A, where the columns of Q formed that orthonormal basis for the column space of A. Okay, so what that tells me is AX hat is equal to B hat, which means that X hat is the least squares solution, because B hat is just the projection of B onto the column space of A. It's the closest point to B that lands in the column space of A. Therefore, X hat is the least squares solution. Okay, which means that the X hat that we came up with up here is that exact solution when we can say that A has linearly independent columns and can have a QR factorization. Okay. So we know that when A has linearly independent columns and can be written as A is equal to QR, that the least squares solution is just R inverse Q transpose B. Okay. Sometimes trying to find this inverse matrix here can be tedious. I mean, you've got a calculator, so it doesn't matter too much. But sometimes computationally it can take a while. So sometimes what they do is actually multiply both sides through by R and then just form this augmented matrix where you've got the matrix R on the left and the vector Q transpose B on the right, and then go ahead and reduce that down to find X hat. That's totally fine. But as I said, you have a calculator with you, so finding the inverse of R shouldn't be too difficult. You just plug it into a calculator. Let's do a quick example. Now, this one is an example that I did back when we did QR factorization in 6.4, okay? I used this matrix and found the QR factorization of it just to make it quicker here. So, we're going to find the least squares solution of AX is equal to B, where A is going to equal 310 and 865, and B is going to equal 357. Okay. Now, I did the QR factorization of this matrix in the previous chapter. So A can also be written as QR, where Q and R were these matrices. So that was Q and R. So what I need to find here, I have R, I really need Q transpose B. So if you go ahead and transpose this matrix Q, and then multiply that transpose by this vector B, what I end up with by doing that is 14 over the square root of 10 and 52 over the square root of 35. If you do want to rationalize these fractions, feel free. I've just kept the square roots on the bottom for now. Okay. And then if I solve R times X hat is equal to Q transpose B, it means that I am solving this system. Okay, so I'm solving that system. So you can go ahead and put this as an augmented matrix in your calculator if you want, and make your calculator find the reduced row echelon form for you. I will tell you what the solutions are. The way that I've actually done it in my notes is just to go ahead and solve for x2 for that bottom line, and just say that the square root of 35 times x2 is 52 over the square root of 35. Divide both sides by the square root of 35 and you end up with x2 is 52 over 35. And then plug that in for x2 and then use this top line to find x1. Okay, so I end up with x1 in that case is equal to negative 107 over 35. So x hat, again, if you do this, you may be able to reduce these down slightly. I haven't checked the factors for it, so you may have to go ahead and look. But that is the solution that I get for x hat. Okay, so this is really easy to do. As I said, if you want to find the inverse of r, you can go ahead and do that. Your calculator will do that for you, and then you could just do r inverse times this q transpose b vector. Okay, you can also do that, and that will find x hat. But r will always be invertible. It's just a case of computationally. Sometimes people like to go ahead and use the Gauss-Jordan reduction. Other people like to go ahead and find the inverse of r. It just takes slightly longer, especially with bigger matrices when you do this, like in coding and stuff. Computationally, inverses take a while to compute, whereas Gauss-Jordan is slightly quicker. Go ahead and try some of these when I give you the homework on Friday. It shouldn't be too bad, but just kind of understand the theory behind it of what this least squares solution is, okay? It's that solution that when you've got an inconsistent system, it's kind of that closest solution that you can possibly find that makes A times X as close to B as you can possibly find, with it still being consistent when in fact you actually have an inconsistent system. Okay. If you've got any questions, please let me know and I will see you in the next video.